Well, good evening, everyone, and welcome to the first talk of the year. Are we running yet? I was supposed to wait for a light. They've given me the light. Okay. Well, again, good evening, everyone, and welcome to the first talk of the year in SD Forum's Distinguished Speaker Series, co-hosted by the Computer History Museum and the Chinese Software Professionals Association. I'm Sanford Rockowitz, co-chair of the series. SD Forum, as most of you probably know, is an organization of some 2,000 software professionals. Its premier sponsors include Microsoft, Sun, BEA, IBM, Oracle, and the capital of Silicon Valley, the city of San Jose. Our aim is to be your single best source of information and connection for all aspects of the software industry. To that end, we have some 12 or so SIGs that meet monthly on topics ranging, if not quite from A to Z, then at least from bioinformatics to web services. In addition, we hold numerous special events, including this series. And so if you're not already a member, I'd encourage you to become one. You have discounted or free access to our 20 to 30 events each month, and additional member benefits such as discounted access to various industry conferences. Laura Merling, who's at the back of the room, is our executive director. And Laura, did you have anything that you want to add?
Thank you. Welcome, everyone.
Great. Next month, I mentioned, is .NET month at SD Forum. And most of our SIGs are going to be focusing on .NET as a topic for that month. Even our Java SIG, believe it or not, is going to be talking about .NET interoperability. Also, another one of our special events next month that I think many of the people in the audience here may find of interest is Richard Taylor, who's chair of our Business Intelligence SIG, is putting together a panel on the future of databases. And Richard, did you want to say anything about that? Oh, okay. Well, October 8th, and it's going to be here, correct? Great. It's the first talk of the year, and so I'd like to take a few minutes to acknowledge the organizations and people that have made this series possible. First of all, I'm delighted to say that this year, as last year, the Computer History Museum is co-hosting the series. And as was the case last year, they're actually videotaping many of the talks in the series for their archives. John Toole is the museum's executive director. And John, you want to say a few words?
Welcome, everyone. It's a real pleasure to be the co-host. The Computer History Museum is one of the preserved artifact stories of the information age. And we've probably got the largest collection of artifacts in the world. And since I saw most of you back in June, we have opened our alpha phase in our new building, 119,000 square feet, formerly the SGI International Sales and Marketing Headquarters at Shoreline 101. And our alpha phase, as good software engineers know, we will have a beta phase and a release 1 and release 2. Subsequent to the time we've got now, we've got a great visible storage. We have public tours Wednesday, Friday, and Saturday. Afternoons. We also have a wonderful lecture series that we have worked together with the Software Development Forum. In fact, our first lecture is September 25th, Philippe Kahn, that many of you, I think, would probably have a very strong interest in seeing. So you're all welcome to attend. In addition, what we're really trying to do is build a research institution. In addition, we've got a tremendous archive, and we probably are displaying probably less than 10% of our artifacts. And of course, our role next year is going to involve a lot of software thinking about what we want to do to exhibit software, how we want to display it, how we want to preserve it. So we can use all of your help, and I look forward to working with you and definitely the Software Development Forum and now in the future.
Great. Thanks, John. Also pleased to tell you that this year we added an additional co-hosting organization, and that is the Chinese Software Professionals Association. Alex Chan, who's the organization's president, is also very active in SD Forum. He co-chairs our wireless and voice SIG, and is also serves on the executive committee. Alex?
It's our honor to be here to host this event. And as you know, CSP is a professional organization, and we organize regular events.
talking about different topics. And one thing that I want to mention to you is that next week, while after you listen to Philip Kahn about all this business and entrepreneurship, and if you are into eating and drinking and mixing with VCs and entrepreneurs, you could come and check out our event. So we'll have an event at Pillsbury Winthrop, which is in Palo Alto, which is one of the law firm. And we will have our professional mixer there on Thursday, exactly 1 week from now, which is on the same day as the Philip Kahn's event. So, and feel free to check out our website, http://worldwideweb.cspa.com, and you can find out more about our events and program. Thank you.
Thanks, Alex. Next, I'd like to introduce some of the people who've worked so hard to make this series possible. In particular, I want to introduce Bebo White of Slack Computing Services, Slack being Stanford Linear Accelerator Center. Bebo has joined me this year as co-chair of the series. And Bebo has an interesting history. We won't talk about the first website. Okay, Bebo helped develop the first website in the US at Slack. He's been involved with the web ever since. Last year, he was conference co-chair of the 12th International Worldwide Web Conference in Budapest, Hungary. He's a fellow of the International Worldwide Web Institute. He's a member of the International Academy of Digital Arts and Sciences. Those are the folks who hand out the Webbies. So if you want to be a Webbie, be nice to Bebo. And he's taught at UC, UCSF, Hong Kong University, and he's co-author of several books on software and web development. So Bebo, we're delighted to have you aboard.
Thanks everyone for coming. We certainly appreciate your feedback on this particular series and things that we can do better in the future. So if you have any comments or questions about the series or things that you'd like to see, I'm sure that Sandy joins me in saying, please come by and corner us and let us know what their suggestions are.
Absolutely. Thanks, Bebo. I also want to acknowledge we've had sort of an informal program committee whose input has been really quite invaluable in putting the series together. One of the members of that committee is Alex Chan, whom you've already heard from. Chuck Berg is Vice President at Rockcliffe Software. Many of you know Chuck as the chair of our Windows SIG. He was president of Software Forum, one of the predecessor organizations for the Software Development Forum. He's a former board member and currently serves on our executive council. And it was Chuck who originally contacted Jim Gray about a year ago about coming to speak. Bill Grasso, who's somewhere here, he's sitting in the back, is Vice President at Hipbone Software. He's chair of the Emerging Technologies SIG, and he serves on the SD Forum's board of directors and on its executive council. And finally, Matt Grasick, who's product manager at Wakesoft, has provided invaluable input. And lastly, I want to mention Julie Larson of the SD Forum staff. Is Julie here, or is she still out? She's out. So Julie is the person who really makes it all happen and handles all of the logistics of events. So I really want to give a round of applause to all these people. The Distinguished Speaker Series is the successor to last year's Future of Software Development lecture series. The series presents people whose leadership and creativity have advanced the state of the art in software development and who've helped us understand the role of software in the larger society. The theme for our 2003-2004 series of talks is As Computing is Everywhere. And during the coming year, our hope is to explore the changes, challenges, and opportunities confronting both software developers and the larger society as software creation, implementation, and use become geographically, organizationally, and technologically dispersed. Some of the talks in this series, such as tonight's, will emphasize the underlying technologies. Others, the social impact of these changes. We intend to consider how these developments both enable and engender new kinds of applications and new forms of social organization, and also allow us to revisit old problems in new ways. Our next talk on the 23rd features Mitch Kapoor. Chuck always smiles at me. Chuck is, or Mitch, as most of you know, founded Lotus 123, founded Lotus, created 123, the killer app of the PC revolution, and since then has been involved in numerous notable activities. In particular, he co-founded the Electronic Frontier Foundation and most recently Open Source Application Foundation. And Mitch is going to be speaking on the topic of ubiquitous open source. What does it mean for the software industry? And also, we're thinking that next month we might try something a little bit different in format as a way of sort of encouraging people to come and talk with each other. And we're thinking we might have actually a little jazz combo out in the foyer for the sort of an hour before the talk. What do people think about that? Like the idea? Okay, well, pardon? Right. The objective is to encourage conversation, not eliminate it. Yeah, so stay tuned to the web page. In November, our speaker will be Will Wright, creator of the Sims family of programs, including SimCity and most recently the Sims Online. And he's going to be speaking about what we can learn from game design. And finally, I want for this finally in terms of this year, in December, we're going to be hearing from John Gage, director of the science office at Sun Microsystems, and the person who created NetDay. So to stay up to date on all of this, I'd encourage you to get on the SD Forum events mailing list. I believe there are sign-up sheets out in the lobby where you can do that, or you can go to our website, www.sdforum.org, and sign up there. Well, now it's my pleasure to introduce the man who's going to introduce our speaker tonight. Geo Wiederhold is Professor Emeritus of Computer Science, Electrical Engineering, and Medicine at Stanford University. His current work revolves around large-scale interoperation, mediation, and composition. He's a fellow of the ACM, the IEEE, and the American College of Medical Informatics. For some 20 years, his Friday database seminar was a key venue where leading figures in academic and commercial database research met to discuss their work. And Jim, you presented there as well. And so, Gio.
Thank you very much. It's a great honor for me to introduce Jim Gray. He's our 1998 Turing Award winner. And I think that was the first database or Turing Award, as far as I know. So it's a very important event, the Turing Award being as close as what we have in terms of a Nobel Prize. Jim founded and runs now the Microsoft Bay Area Research Center, research lab that focuses on scalable computing. And an example of that is a Terra server. You can get pictures of your house. In fact, I have gotten pictures of the house from top on Terra server and how to find it. And now they also have Sky server. And I guess that's to help aliens find their way back home or something like that. Being an oldie, I'd like to focus on some early events in Jim's life because the problem is those you don't find on the web. In 1974, that's the first time I encountered work, was an IBM research report jointly with Esperan and Laurie on predicate logs, essentially for relational databases. That became the 1975 classic paper in the National Computer Conference with Chamberlain and Traeger, but your name wasn't on it for some reason. But then the paper was further revised and appeared in 1976 in the CACM, again with Jim's name on it. It's a classic paper on System R. Much further work by everybody has been based on that paper. That was published, by the way, at a time when IBM salesmen were still telling their customers that relational databases are nice for researchers, but they'll never beat IMS. You know, of course, well, eventually relational databases chopped a big economic hole into the IMS and similar technologies. And the simile that I'm thinking of is from the Marion Winslet interview with Jim Gray, where Jim Gray describes how he chopped a hole into his sailboat that he wanted to get rid of because he had a better sailboat at the time and only wanted to pay one slip fee. And nearly every year for some time, there was an important paper. There was a paper in 75 on granularity of logs with Laura and Putzula, active IBM research report, which was an issue that was actually seriously addressed only 10 years later. There was another paper on the use of assertions. You gave a course at the Technical University in Munich, right? Sponsored by Rudy Bayer. That's a Bayer from the bee trees fame. Although Rudy says he refuses to say that he named bee trees after himself because he was working at that time for Boeing, and it was also balanced trees. So there's 3 reasons for the bee. In 1979, a paper on the recovery manager. Again, pretty amazing because IBM didn't have any databases to recover from then at that time yet. And in 1980, paper on the transaction model, and then the recovery manager of System R was described in 91, also an article in the NATO volume, and then more work on the transaction concept, which was actually then reprinted by a fan of Jim Gray's Stonebreaker in his later collection. So that's relatively more accessible. Also more accessible is then a 1982 paper on transaction consistency with Irv Traeger, Bruce Lindsay, and Cesare Galtieri. Cesare Galtieri was the architect for the IBM Advanced Systems Design project. Was here on Sand Hill Road. I don't know whether Jim ever visited it. When IBM canceled the project and the building became available, it was actually rented for some time by Relational Software Incorporated, which eventually became Oracle. And I wondered whether some DNA of Jim's found its way into Oracle that way. In 1985, Jim was part of Anonymous et al. I don't know why they didn't want to give the names. Measuring Transaction Power, a paper in Datamation. I think that was about the time that you switched to tandem computing. And so then there were a number of useful case studies and benchmarks on tandem. 1987, a major opus, a book on transaction processing with Reuter, German professor. In 1987, and that's a good way to stop, there was a paper on the 5-minute rule at Sigmod, and I think a 5-minute rule is a good limit for an introduction. Thank you, Jim.
I have this feeling my life is passing before me. Thank you. Thank you, Jim.
But you didn't have to die to do it.
That's right. Well, first, thanks for coming. I have a 20-minute talk. I'm going to stretch it out to more than 20 minutes. Let's see. Did I screw up? Is it me? Probably is. Patience. Let's hope for the best. Yep. So I'm going to talk to you first about distributed computing economics, and then I'm going to fill if nobody argues too vehemently with me, and so it only takes the 20 minutes that it should take. I'm going to try, there's a paper at that address. It's a technical report with that title, Distributed Computing Economics. And it tries to explain why SETI at home is such a great deal. SETI at home is an extremely good business proposition. There are others on the internet. Why Napster is such a good deal. Why the computational grid is not an especially good deal for most applications. It is for some. I mean, SETI at home and Napster are examples of computational grid. When does computing on demand work? You've been hearing a lot about computing on demand or on-demand computing or something like that. And what's the right level of abstraction for building an application on the internet? And is the access grid a real killer app for the next generation internet? So the first thing, and I'm going to use a prop through all of this. This is my prop. So if you know how to shop, you can buy a computer for $1,000. Yes, I know you can buy a computer for a lot less. I know you can buy a computer for a lot more. But you know what I mean. If you go over to Fry's or you go to Dell or something like that, you can buy a pretty substantial computer for $1,000. And it'll last you for about 3 years. And that's about 1,000 days. So a day costs $1. This is 1 day's worth of computing. With me so far? Well, you know, it's interesting. People say, oh, what about the power, right? So, well, and it depends on what you know, whether you're Gray Davis and you're buying power or you're, you know, somebody else and buying power, okay? So this might buy you a fraction of a kilowatt if you don't know how to shop, okay? But if your computer uses 100 watts, then this is, you know, in 10 hours it uses a kilowatt. And so that's a tenth of this dollar. Okay? And you still got quite a few dollars left. And so, you know, 2/10 of a dollar or 20% is power. Okay? People and floor space and other things are, you know, networking is going to turn out to be a bigger deal than I think. Okay? Now, if you pay the phone bill, and I do, okay, you can, again, shop in a variety of ways, and you can pay between $50 per megabit per second per month and $500 per megabit per second per month. Now, I know you could pay more than that, but Brewster Kahle, who's my smartest shopper I know, is able to get it for $35 a megabit per second per month. And some people who remain nameless pay $80 a megabit per second per month. And it's easy to find people who are paying $500. Okay? This does not include the routers. It does not include the operations staff. It does not. This is what you pay to the phone company or your internet service provider. With me so far? So you do some sloppy math, and you conclude that if you use that wire all the time, every day, for the entire month, it would cost you $1 a gigabyte. So 1 day of CPU equals $1 equals 1 gigabyte on the way out, or conversely, 1 gigabyte on the way in. And that $1 for the gigabyte is for the low end of that price range. That is to say, if you're paying $500 a megabit a second a month, then it's going to be $10 to send that gigabyte out. And if I'm paying that rate, it's going to be $10 to receive it, or $20 per gigabyte instead of 1 or 2. With me so far? And you have to appreciate at the bottom, all these numbers are rounded to the nearest factor of 3. Okay? You understand what that means? I mean, I'm trying to, don't talk to me about pennies or even, you know, factors of 2 or 3. But if factors of 10, I really worry about. And you'll see that it's factors of 10 to the 5th that I really, really worry about. We'll come to some of those. So why is SETI at home such a good deal? Well, it's easy. SETI has a problem. Okay? Its problem can be stated in 300 kilobytes. How much does it cost for me to give you 300 kilobytes? Well, it costs 1,000th of a gigabyte is a megabyte, and it even costs less than that. So it costs like $1 milli or 300 microdollars for me to send you the question. And now you compute for a day. And you give me $1 worth of CPU. So I invest $1 milli and get back $1 worth of value. What a fantastic deal. Great ROI. You know, Warren Buffett would like this investment. Okay? So SETI at home, in round numbers, has spent a few $1 million in bandwidth, paid for by the University of California, incidentally. At one point, they were 30% of the UC Berkeley bandwidth. But they've gotten a few $1 billion of CPU time out of it, valued as I was describing. Just to give you a sense, the SETI at home is the world's most powerful computer. People talk about how, EarthSim is 53 teraflops on a good day, and actually no one's ever actually seen it run more than 38 teraflops. This thing is running at 60 teraflops early this year, and probably more now. Okay, it's 1.5 million CPU years total. It's a heck of an interesting problem that they're working on. Okay, so why is Napster a good deal? Well, it's a similar story. I can give you a song for half a penny, and frankly, many people are willing to tear a dollar bill up just to make a point. I mean, a half a penny is nothing. So the networking associated with distributing songs or distributing anything on the internet that's in the kilobyte or megabyte range is trivial. It's in the milli-dollar range. It's only when you get up to the terabyte range that things start looking expensive. Both the sender and the receiver can do this transaction at essentially zero cost to either of them, and there's some benefit to one of them. A similar logic powers the likes of Yahoo or Google or something like that. If the numbers vary, but if you have a website, people will pay you, in round numbers, $1 for every 1,000 impressions or eyeballs that you deliver. Sometimes they'll pay you $10 if you're doing really good eyeballs. Sometimes they'll pay you 10 cents if you're delivering really bad eyeballs. Okay? But $1 is a reasonable example of what you can get by putting up a web page. So, I'm sorry, 1,000 web pages, excuse me. So a milli-dollar is what you get for one web page. So if you can deliver a web page for a microdollar, you've got 1,000 to 1 return on investment. And in fact, your goal in life is to generate as much traffic as you can. So you generate as many impressions as you can. So that's one side of the equation. That's the revenue side of the equation. And you'd like to do that as cheaply as possible. And profit is revenue minus expense. Okay? And if it's 99.9% revenue, you're in great shape. So people who can generate content that lots of other people want to look at have a great business if they can generate that content for free. Google's an example of a company that generates content almost for free. Hotmail is an example where one customer generates the content and another customer uses the content. So Hotmail's figured out how to get the customers to generate the content for the other customers. And Yahoo is a similar thing with Yahoo Mail. So there's various strategies for getting eyeballs to look at your stuff. Gio mentioned the Terra server. The Terra server is, the USGS went out and spent several $1 billion to take pictures of people's houses from airplanes. And we took that stuff and for not very much money put it in a computer. And we can serve up the contents of the Terra server for in the range of milli-dollars per page. Fundamentally, the content was paid for by somebody else. Does all this make sense? Okay, so there's a paradox here. If computers are free, how come they cost so much? Okay, you can buy a $10 million computer. I told you could buy a computer for $1,000, but it is possible to buy a much, much more expensive computer. And people do it, especially large corporations do it. And there's a benchmark called the Transaction Processing Performance Council benchmark. And if you can go and look at the kinds of machines that are at the high end of that benchmark, and they are indeed in the millions of dollars range. Interestingly, almost all the money goes to storage. If you look at that pie chart, it's 61% storage, and by that I mean disks and disk controllers. about 30% CPU and memory and power supplies and sheet metal and all the stuff beside the storage. Incidentally, I should have said networking in there. That's, the networking gear is actually a relatively small part of the cost of those systems. And then there's a substantial fee that the software guys charge, which is like 10%. Okay. So this is an interesting pie chart, and it tries to get across several points. One is that, in fact, there are very, very expensive computers. The computers are not expensive primarily because of the processors. They're expensive primarily because of the storage. And they're actually expensive because of this. Computers routinely live in buildings that are almost as expensive as the computer. And that's rolled into the capital cost. And then if you take the other costs that the organization pays, it's people costs. So 60% of the money goes to people, and 40% of the money goes to the building and the power and to IBM in this case. Okay. So this observation, and in particular this observation, the 60%, is what is powering the desire to do computing on demand. Everybody who works with computers knows how inefficient they are. They know what crappy job they're doing. They know how much waste there is inside their company. They can't help thinking that somebody else knows how to do it better than everybody else knows how to do it better than they do it. So, you know, you just can't imagine that as bad as it is where you are, it actually could be worse somewhere else. So in particular, one theory is that if we could just get somebody who's smart to operate our computers, it would be much cheaper. And in particular, an example of this is that you go to Wall Street and you say, how much does it cost to manage a terabyte of storage for your company? And people routinely say, $500,000 a year to manage a terabyte, $100,000 a year to manage a terabyte, somewhere in that range. And they have data administrators, and they have staff, and they do backups, and they have all this careful stuff. And then you go to, say, Yahoo or Google, and you say, how many terabytes do you have? And they say, well, we don't know exactly. Hundreds, thousands, somewhere in that range. How many people do you have managing them? Well, we don't know exactly. 10, 20, you know, somewhere in that range. But it's the ratio of staff to terabytes in, say, Hotmail, Google, Yahoo, these places, is 1 person per 100 terabytes, as opposed to 3 or 4 people per terabyte. Now you might say, well, the people on Wall Street are, you know, have very valuable data, and the people at Yahoo have not very valuable data, or so on. But the fact is that a terabyte holds, in round numbers, 1 million people's mailboxes. And there must be a lot of people in those million who are not very important and aren't going to scream very loud if you lose their mailbox. But I think the aggregate of the million will scream pretty loud, a lot louder than the typical Wall Street guy if you lose a record. So in fact, the people at Yahoo and the people at Hotmail and the people at Google are actually very careful about not losing information. They don't care about losing bytes, but they use massive redundancy, and they trade hardware for operations cost. So there is this theory, and I think there's validity to the theory, that there are better ways of operating computers than the traditional ways, and that perhaps if we could outsource our computer operations, we could save that 60%. So computing on demand is really, I believe, a bet that somebody else could do a better job than I can managing my computers. Okay. But we'll come back to that in a moment and just talk about the equivalence of what this dollar would buy you. Okay. So I explained to you it'll buy you a day of CPU time. It'll buy you about 4 gig of RAM for a day, fairly high-speed RAM. It'll buy you a gigabyte of network bandwidth, a gigabyte of disk storage for 3 years. So basically a digital graveyard for your gigabyte. And it's interesting that the same price for storing the data for 3 years or for sending it over the network. So this is a surprising trade-off. If somebody sends you a gigabyte, you paid $1 to get it. If you're ever going to access it again, you should save it, because it'll be faster to get it off the local disk than to get it across the network. Okay? Personal video recorders, I think, are just an instance of people doing that. You can have 10 million database accesses for this $1, 10 terabyte of disk accesses, which is to say disk bandwidth, and 10 terabytes of LAN bandwidth, moving stuff across the local area network. And somebody asked about power. It's basically about 4 days of computer time, 10 kilowatt hours, if it's 10 cents a kilowatt. And all this stuff is done by depreciating over 3 years. So what's the consequence of that? Some consequences of it. Remember I said that I thought that 10 to the 5th was important and 3 was not so important? Beowulf networking, or LAN networking, is 10 to the 5th cheaper than WAN networking. The cost per byte is 100,000 times cheaper. The cheapest and fastest way to move a terabyte cross-country is via sneakernet. So I've been working with a bunch of astronomers, and we have data sets that are in the terabyte range or multi-terabyte range. And I can write the data to a computer in my office, and I can call up UPS, and the next morning that computer will be in Baltimore, Maryland. Okay? And if you think about it, that's 4 megabytes a second. Okay? And if I write 2 terabytes, it's 8 megabytes a second. And so on, right? Now, if I... You know, that's interesting. So DNA is only a gigabyte. So I think it actually doesn't make a difference. So well, I think I'm glad that you have the right attitude about this. So literally, this is the way we're moving data around. It's faster, it's easier, it's more reliable. If you've tried to FTP a large file, you know that the chances of your terabyte getting FTP'd in the time it would take to do the FTP is small, because something bad is going to happen in the middle, and the restart stuff in many of these utilities is not very good. So in particular, something that your tax dollars and mine are paying for is this. The people at CERN and the people at Caltech want to exchange 10 petabytes per year. And they're actually planning to do this over phone lines. This is not time-critical data, incidentally. These are events that are coming out of the LHC, the Large Hadron Collider, at a pretty bodacious rate. The people at Caltech need to buy disks to store this stuff on. Plan A. People at Caltech buy the disks to have them drop shipped to CERN. CERN fills the disks. CERN ships the disks to Caltech. Okay? Plan B. The people at Caltech buy the disks at Caltech. They pay a huge phone bill to move the stuff to Caltech so they can put it on the disks that are at Caltech. Okay? The current plan of record is Plan B. Sure. Lots. Questions are good.
There's supposed to be an unbelievable boatload of dark fiber in this country.
There is.
So how does that happen? How come we're not lighting up the dark fiber?
Well, so the question is, why? There's all this dark fiber. There's dark fiber in front of my house. There's dark fiber in front of my office. Why isn't it lit up? Why is it that we're paying these outrageous fees for fiber?
Diego and Geneva would have enough bucks to get a tap into the dark fiber.
Right. So lighting the fiber is not cheap. That's okay. And you'll say, bullshit, and you're right. Microsoft, for example, I work at Microsoft, has a ring around Seattle. We bought some dark fiber for $5 million around Seattle, and we are lighting it. And the return on investment was like a week and a half. Okay? I mean, literally. I mean, it's phone bills are just huge. How could this be? Well, there's tariffs, and there's phone companies. And phone companies' core competence, as far as I can tell, is lobbying. Okay? 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 And I'm serious about this. So they look at the situation, and they say, one fiber as a bandwidth of a few terabits. Okay? Okay? Now, right now, we're only at 50 gig, but that's because we're not trying very hard, and that's only one lambda, and et cetera. Okay? Okay? But 1 terabit, 5 terabits, somewhere in that neighborhood. Okay? Now let's take, there's 6 billion people in the world. Let's imagine that everybody calls somebody else. Okay, there's 3 billion phone calls. They will all fit in that one fiber. Okay? Now, the phone companies make money on telephone calls. And they are terrified of the notion that one fiber would carry all of the traffic on the planet. So they price that fiber as though it's a voice equivalence. And the whole structure of pricing seems to be based on this voice equivalence stuff.
Tariff to protect that.
Right. Now, this has to end someday. Well, De Beers keeps charging money for diamonds that you think it hasn't ended, but John Stuart Mill says that it has to. I mean, John Stuart Mill said, I know. In the end, we're all dead. But in fact, I think in the end, rationality has to prevail. But what fundamentally has to happen is all these companies have to go bankrupt because, in fact, there's a gap between what they think they're worth and what they're actually worth. Now, go ahead.
Seattle lights it up for its own use, and does the same thing in the Bay Area again for its own uses, and then connects them together for its own uses, and then says, hey, why don't we just let everybody in the Bay Area and Seattle want to talk to each other, hop on for pennies a year.
That's where the tariff came in. They can't do that. They can talk to themselves, but they can't talk to anybody else, and they can only carry data. I'm sorry?
Microsoft has more money than the phone companies, so maybe Microsoft would be.
Well, you have more money than the phone companies. They're all bankrupt. I mean, all right. That was a good question. That was so. I'm glad to see that you guys all have the right attitude. Right. So this is just, a reality check that if the phone companies all went bankrupt, and if we had this new world where, in fact, this was relatively cheap, then we could move terabytes around in minutes. But we are not here. Okay? This is actually 1/4 of a fiber. Okay? This is 10 gigabits as opposed to 40 gigabits. So this is 1/4 of a lambda. These slides, if somebody's taking notes, these slides are all on my website or will be tomorrow morning. Okay. Nearly free networking, an alternate reality. Telcos go bankrupt, and so price equals cost equals 0. Okay? Like computers are free, right? So bandwidth would, as we think of bandwidth, would be free. Voice at this point is free. It's data that, in fact, you pay a lot for. Okay? But a separate reality is that you work for a government lab. And so the taxpayers pay your phone bill, and so the price equals 0. And the telcos get big government subsidy. And that is actually the reality we're in now. Well, I mean, okay. So, to the extent that the computational grid is like SETI at home, and I explained why SETI at home is actually a good thing, even if you're paying the phone bill. If you're paying the current tariffs, SETI at home is a good deal. Right? IBM has something called ZetaNet. What ZetaNet is doing is computing zeros of the zeta function. Billions of zeros are known. They've computed a few more billions of zeros. Okay? And if a processor isn't doing anything, it sits there and computes for a few days and produces a few more zeros for the zeta function. Okay? And so it's days of computation and bytes of answer. Okay? So it's a great thing, but for example, RenderMan or render farms work great on Beowulfs, but they would not work very well on the internet with the current pricing of bandwidth, because I think the next slide explains what the ratio is. So to the extent that a computational grid, where you want to take your computation and spread it out over a bunch of computers in the internet, and use MPI programming, the message processing interface, the kind of typical thing that the science community does, it's just not economic, because it costs you a lot in phone bill, and you don't get much benefit in computation. You know, the line there is the internet is not the CPU backplane. So here's the algorithm. Okay. If the instruction density, that is the number of instructions you execute per byte of network traffic. I'll say that again. The number of instructions you execute, the CPU time per byte of network traffic. If it's greater than 100,000, ship it. Oh, and if the CPU at the other end is free, okay, then it's a positive ROI. If you have less than 100,000 instructions per byte, it's a negative ROI. You with me? Okay. So most of the people I work with, RenderMan is just a little bit under 100K instructions per byte, ray tracing kind of things. The astronomers I work with, they're looking for galaxies and doing point spread functions and doing curve fitting and basically doing vision on pixels. And they're at the 10,000 instructions per byte density. And MPI, if you look at it, is way, way down in the instructions per byte, which is to say 1,000 instructions per byte, 10,000 instructions per byte for a typical MPI program. Okay? So fundamentally, this is a way of saying, okay, if you have a computation, when should you do it in the cluster, and when should you try and ship it out into the wider internet? And the answer is this. Now, of course, this algorithm and this equation changes depending on the cost of processing and on the cost of networking. Oops. I should stop there. This is.
Now, I've lost the memory of the ratio between what the tariff says and what a
I didn't say.
Yeah.
So the question is, so what's the real cost of networking versus the tariff cost of networking? So it's been pretty easy for me to be fast and loose because the tariff cost is so high, and hiding behind the tariff cost is the cost of the Cisco or 4 or Catalyst switch that you have to buy, and those things are incredibly overpriced as far as I can tell. And then there's the network engineers that sit behind those, who are the high priests of networking, and they are more expensive than the switches. So if you look at the pie chart of where your networking costs go, it looks horrible that, you know, gosh, look at that huge phone bill. And then you dig into it and you find out that, oh, that doesn't include the routers and all that stuff that I have to buy. And then the people who run all that stuff. No, the dig up the streets guys are included in the cost of the fiber, and that's Raj knows that number, but I remember numbers like $100 a meter or something like that. I mean, they're small. The capital cost of the fiber is actually small. Please don't quote me on that. That's a number that it comes to mind, but I don't think it's right. If you want to know that number, ask me an email, and I will get you the correct number. Yes, the right-of-way can be expensive unless you happen to be Southern Pacific, or unless you happen to be the Department of Water Resources in California, or unless you happen to be AT&T, or, you know. And so there's people who have right-of-ways all over the place, and they'd all love to monetize their right-of-way. So, so what you asked, I see factors of 6 inside my company between the phone bill and the end user cost because of the cost of the, so if the price of the phone line went to 0, inside your typical company, it would be a 10% savings.
So this number still holds if the fiber is free. Right.
Yeah. Well, yeah, maybe. I mean, if you can avoid having network engineers, avoid having network engineers. But you can't. Okay? So this goes back to the topic I mentioned earlier. Wouldn't it be nice to not have any IT staff? Wouldn't it be nice if you could just get applications on demand? And in Gio's youth and my youth, there was something called Computer Sciences Corporation, which I believe still exists, and it was an outsourcing company. Yep. And there was this company, IBM, that used to have a service bureau, and there was a Federal Systems Division that was a service bureau, and it goes on like that. So this used to be called outsourcing or service bureaus, and it's the wheel of reincarnation. This idea is back. And it was popular in those days because computers were incredibly capital intensive. And time sharing made very good sense. And staff sharing made very good sense. Well, computers are less capital intensive than they used to be, but they're still very staff intensive. So if you can figure out how to outsource your app, and if you can find somebody who is as efficient as Google or Yahoo or Hotmail in operating the large data centers, then they can probably do it better than you can. Appreciate this is not a new way of doing things. Virtually every company outsources payroll. Payroll is an application. Many, many, many companies outsource most of their HR, 401k, that kind of stuff. Okay? Salesforce.com outsources many of the things of automating your sales force. Oracle.com, Oracle has a bunch of applications, and they make the following argument. Look, we're Oracle, we understand databases. We're Oracle, we understand Oracle apps. If you want to run Oracle apps, we can do it better than you can. It's hard to argue with them about that. Okay? And they're willing to run Oracle apps for you, and they're willing to do it and make you the promise that they can do it cheaper than you can, and they can give you better service than you can. Okay? But appreciate that Oracle apps are things like accounts receivable, payroll, HR, things like that, which are, again, these fairly standard apps that are, like General Ledger that have been around for a good long time. They're not Amazon.com. They're not Expedia. They're not Amex or Walmart or E-Trade or eBay. If you think about it, I think eBay's core competence is the services they offer. They're constantly inventing new services. They're inventing new ways of doing things. So if you ask, eBay is not especially good at operating computers. I don't mean to criticize eBay in any way. It's just that that's not, they don't need to run their data center, okay? But they do need to do the software that goes into their data center. So they need to be the people who do the apps. Parenthetically, Microsoft runs MSN, and we contract out much of the, we are hosted by Exodus at MSN, and we contract out much of the operations stuff for MSN and for our things. So Microsoft, for example, does outsourcing of certain things. They certainly don't do outsourcing of writing the Hotmail applications or, in fact, operating the applications. So computing on demand works for standard applications, and it works for commoditized services, but it doesn't seem to work for these things, or at least that's my premise. Okay. Where it works is where there is someone who can operate the stuff less expensively than you can, okay? And where it's okay for them to be operating it because it's not a core part of your business. So let's suppose, and I should mention that, at least in the paper, I took a pot shot at LoudCloud and said, look, people have been talking about computing on demand and outsourcing, and in fact, LoudCloud is a recent startup of somebody who said, look, we are going to build a company and we're just going to be really great at operating systems for you. Okay? And the whole application service provider market, LoudCloud being the most visible instance of it, hasn't worked out very well as a business. Margins stink. It's hard for you to do better than the IT shop inside a company. Not impossible, but hard. And in fact, historically, nobody's done very well at it. Gio, you've got more history about this. You want to add to this? You probably know more about it than I do.
If you do the maintenance right, because so much of the cost is maintenance, but then it's not just operating, you know, an anonymous service. It is keeping the payroll works, because there's a lot of work in keeping up with all the state rules, all the government rules, etc. Much cheaper to do centrally than do it at home. It, you know, so if you have applications like that, where there's much maintenance or perfection, where people always expect slight improvement, but it's the same everywhere. So it depends whether you have a maintenance-intensive service, and then you can suddenly now make money of maintenance, which in your own shop is an utter pain.
Yep. One of the nice things about outsourcing I should mention, which I read these things about, this company just signed a $10 billion outsourcing agreement with so-and-so. Okay? Well, that's usually over 10 years, so it's $1 billion. That's cool. And what usually happened is 1,000 employees from company number 1 have transferred to company number 2. Okay? And what this means is the company number 1 has got the capital off their books, they've got the employees off their books, and they've got a liability to pay $10 million over the next 10 years, which they would have paid out anyway somehow. But now their books look a lot nicer. The receiving company doesn't make these employees real employees. They make them contractors in some way, and 30% of those employees disappear after a year. And it's some of these outsourcing things are really absolutely brutal for the IT industry.
Furthermore, often have the largest cash paid to the outsourcing company, which boosts their income for that year, which helps the executive's bonus.
Okay. So there's a lot of hanky-panky in these giant outsourcing deals that you hear about. Okay. Back to things more technical. So as a designer, what interface do you give across the internet to your application? Okay. Do you give bytes, disk block number 7? Do you give files, file so-and-so, a directory tree, WebDAV? Do you give SQL? Okay. Do you give RPC? Or do you give application? Application being a blast search from the National Center for Bioinformatics, or a Google search from Google. Okay? I have strong opinions on this. This is better. Okay? I'll try to explain. I'm actually going to talk to you in a while about the Sky Server. Gio and I have been looking for most of our careers for a distributed database. I've finally found a distributed database after all these years, and here it is, the astronomy data. But it's really, absolutely, honestly unique. The Terra server, what people actually want of the Terra server is something much more like a web service, but it's an RPC-like thing, and I'll show you that in a while. So this just restates the previous slide. Disk blocks are too low a level of abstraction. Among other things, they're at the wrong end of that equation about how many instructions per byte. Okay? You could execute 100,000 instructions to give the guy the answer. So if there's something in that disk block he wants, he should ask you what he wants in that disk block, and you'll tell him 42, okay? Which is the answer to all questions, of course, and smaller than a disk block. Yep.
Probably, this is implicit in what you said, I'm sure, but I just haven't gotten it yet. Say you've been looking for a distributed database your whole life, and you found this Terra data, and it's pretty much unique. There's stuff like Napster out there, which I would argue is a distributed database, or am I missing something?
No, it's a distributed application.
Okay.
Okay. Google is a distributed application. They're serving up objects, and the objects have metadata. And you go to Napster and you say, I'm looking for a song by a group that's, you know, how do you spell Grateful Dead? You know, and so Napster is a search engine and a directory service that eventually gives you a pointer to an object, which then you download. Okay? And Google is similarly, it's not giving you disk blocks. I mean, you go to Google with a web service interface or an HTTP interface, and you pass it some parameters, and it gives you back the answer. It doesn't give you back SQL. It doesn't. I mean, database guys are real clear about what database means these days. SQL, IMS, DBTG. You know, so ODBC interface you'll see what I mean in a while. You'll start giggling when you see this.
People's bosses want the core applications outsourced, no matter how stupid it happens to be.
Yeah.
And it's driving a lot of what's going on.
Yeah. Want to say that again? The microphone. Speak into the microphone.
People's bosses, for some reason, want their core applications outsourced. They're scared of them.
So that was a Dilbert-esque comment about, the pointy-headed bosses want to outsource the core applications because they're so important. And the theory is that other people could do it way better than we could because they're smarter than we are. Okay. So I'll come back to this in a while. Looks like we're going to have enough time. But the point is that web services or EJB or RMI or IIOP or something like that or Corba is in fact a very convenient way of building distributed apps. It gives you an object model. It allows you to export objects. It's wonderful. And it's much more appropriate for the likes of, I have a protein sequence, tell me all the things that are like this protein sequence. I have a sequence of tokens, give me all of the pages that, okay. Email is here's an object, put it in somebody's mailbox. Here's the name of my mailbox, please give me my mail messages. And I'm going to talk about the Sky server in a while, Sky query. Okay. So I'm almost to the end of this distributing computing economics. A really good question is, what comes after the telephone? The telephone was really a good way of improving human communication. It was fundamentally what came before it was either telegraph or letter, depending on how you feel about things. Rumor? What comes after the telephone is rumor? Rumor, okay, voice, right. Yeah, yeah.
People forwarding through informal things, information.
Right. So, if, frankly, for teenagers, the answer is instant messaging. Teenagers used to go home after school and call each other on the telephone, and now teenagers go home and do instant messaging and buddy lists. Yeah. Okay? And for me and for my colleagues and my generation, it's email. I mean, I have these email exchanges with people where it would have been much better to pick up the phone. Okay? But frankly, both of these seem like retro interfaces to me. I mean, my premise is that looking back 100 years from now or 500 years from now, they will not say that instant messaging came after the telephone, but they will say that the telephone or telegraph, or maybe they'll lump telephone and telegraph and email all together as being, electronic communication. But the quality of interaction between people over the telephone is not very good, which is why you folks came to this lecture, is because there's something that goes on in actual face-to-face communication. I'm not sure what it is, okay? And I get in airplanes and go places, and it's crazy that we have all this travel. And there ought to be something that we could do to make it better. So we've been trying to do teleconferencing of some sort, or groupware, or, and people are groping around for the answer. But it is possible that, well, let me put it another way. All of the teleconferencing I've dealt with has been very hard to use, has had absolutely terrible audio fidelity, has had terrible video fidelity, and has just been generally a painful and exhausting experience, because the delays completely screw up all of your intuition and all of the ability to interact with people. So one of the things that I think is possible and is that, in fact, although we're building the high-speed network and the next generation internet for the traditional apps that we see, that the real killer app here might be something which is a teleconferencing.
They used to.
Instant messages anymore.
Yeah. Maybe? Yeah, I mean, they love instant messaging. That's right. Okay, so here's the first 20 minutes, which we managed to stretch out to more like a half hour. Why is study at home a great idea? Because it has very, very good instruction density. Okay, it has 10 million instructions per byte as its instruction density. Why is Napster a great idea, or why was it? I mean, they're not around anymore. Well, it was because you could exchange songs for half a penny, and certainly it was worth more than half a penny. The computational grid is uneconomic unless you can get this great instruction density that we were talking about. Computing on demand works for things that are commoditized. The right level of abstraction is objects, I believe, not disk blocks. And killer app. Okay. So what's the protocol? I could go on for another half hour talking about astronomy stuff and programming stuff, or we could stop and argue, or sure. Sure.
Do you have any historical data on prices? Because what you've just done is you've taken a snapshot and said, at this point in time, $1 buys you this and this, and therefore.
Yep.
What's the trending there?
Well, it's hard. I have lots of historical data, but nothing nearly as good as Andrew Odlyzko, who's at the University of Minnesota, who's done a lot of work on this and is writing and I strongly recommend that you go to Andrew's site and website and look. ODLYZKO. ODLYZKO. And Andrew starts with, let's see, he starts with ancient Rome and their freight rates and their mail rates. Okay? And he works his way forward, and railroads are very interesting. So he's got railroad pricing in there. And he's got telegraph pricing and a few other things, telephone pricing. And ODLYZKO, Odlyzko. It's Google. You won't have a hard time finding Andrew. There's not a lot of guys with that kind of name. He's at a university though. I think is the straight answer. When I first started chatting with when I first became aware that this was such a horrible problem for us, I was seeing prices in the range of $300 per megabit per second per month. And that was about 6 years ago. It was 86, 7 years ago. 2 years ago, it was $100 per megabit per second per month. So it's been dropping at about a factor of 3 every 2 years. Okay? The prices are dropping very, very, very fast. But the CPUs are getting faster very, very, very fast. And so you've got these funny things. And Gio mentioned something called the 5-minute rule that I did in 88 or something like that. In 98, I did a paper called the 5-minute rule 10 years later. And I tracked the ratio between RAM and disk over time and did predictions forward. And much of this economic argument that I've just been through works for other aspects of system design. You can trade disk accesses for RAM, for example, and do the economic trade-off. And it is surprising that the ratios do change. And incidentally, if the ratios don't change, nothing changes. But certain things are constant, like the speed of light. Certain things are getting more expensive, like people. And certain things are getting cheaper, and the rates at which things are getting cheaper vary enormously. For example, disk capacities have been going in half almost every year in the last decade. Sorry, doubling. Disk capacities have been doubling. But access speeds, or bandwidth, has been growing up as the square root because it's areal density. And so, and rotation speeds have been improving, and disks have been getting small, blah, 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 blah. But the net of all of this is that the disks have been getting relatively bigger compared to bandwidth. So that's a place where the ratios have changed pretty dramatically. As far as I can tell in networking, the rest of our technology has been improving faster than the price of networking. Another place where we're lagging is in displays, display real estates. Displays are not getting, twice as many pixels per so on, and batteries. Battery density has not been improving, and this is a big deal for mobility and things like that, and power consumption. Sure.
So, big announcement recently about Oracle 10G.
Mm-hmm.
And, I've been thinking about, you had this slide a few slides ago about whether database is the right level of abstraction versus applications. And the model, the only pricing I'm aware of is what Oracle charges, for example, for say, if you wanted 200 gigabytes of database. And so they will say, okay, for $72,000 per year, you can have 200 gigabytes of database managed with a DBA and server all taken care of. They don't talk much about application pricing. And I think what the argument you made was that it really doesn't make sense to have your application at your site and the database at their site.
Yes.
So can you debunk this?
Okay, so to repeat, people may not have heard the question, but Oracle had Oracle World was last week. They had a very big announcement. Oracle 10G came out. Lots of really neat things in Oracle 10G. POSIX regular expression handling. No, look, I'm a programmer. Well, hey, that's useful. My product doesn't do that. I'll tell you, I'd die for it. So, a lot of just nuts and bolts kinds of things. But Oracle said, this is our grid release. And grid is cool right now. And Ian Foster was there and gave a very good talk. And but what Oracle has done, everybody has taken the word grid and redefined it to mean what they want it to mean. Okay? So Microsoft has redefined grid to mean .NET. Hey, web services, internet scale distributed computing. Hey, and I'm not smiling. I got a straight face. It's true. Okay. Okay. So what Oracle has done is said, look, we make Linux unbreakable, and Oracle is actually making clusters work, Beowulf-style clusters. So they have. Shall I keep blabbering, or do you want to?
No.
Okay. So I'm not trying to explain. Well, I guess I am trying to explain Oracle's marketing strategy. So, my interpretation of what they've done is they've said, look, we use Condor for our regression tests. We use Condor for our builds. Condor is a great thing. It's a batch job scheduler for a bunch of idle processors lying around. Frequently we have these big tasks, database searches and other things, which if we could just break them up into a lot of little jobs and put them in a queue and have them scheduled, that would be great. And so much of what Oracle is calling grid computing is what old guys like me would have called Beowulf computing. But Beowulf computing is dead. It's old. It's 90s. And grid is new. And so that's my understanding. Oracle is a web service. And so it's a .NET-like thing, and but Oracle exports not so much SQL as stored procedures, which are written typically in Java, and they are an object server as well, but they're outward facing onto the internet thing, but internally they just have a cluster and they spread Oracle around among the nodes of the cluster, and they will in fact take your jobs and manage them and run them for you. And incidentally, they've built a file system that is, scalable. And so they've done, actually, I think, a pretty good job of in bringing Beowulf forward the next step. And I think they'll run with that for a couple of releases to come, and it will be a good thing.
Let me just ask, do we want to segue into the Q&A at this point, or do we want Jim to talk more about the Worldwide Telescope? Q&A? No. Slides?
Okay, we're going to have the applause meter.
Or Joe, did you want to say something?
Oracle does another way of outsourcing also, which avoids the bandwidth problem, because if you buy Oracle and Oracle applications, run them on your local machine, you still don't have IT staff anymore to maintain it. You count on Oracle maintaining that software for that 15% forever and ever and ever. And so now you have avoided the bandwidth transmission cost, but you've gotten rid of the 60% of your IT staff, or maybe reduced it
Oracle.com is
to 6. But no, I'm not talking Oracle.com. I'm talking Oracle applications that you run on your machine. And you have gotten rid of most of your IT staff.
One more question and we'll plunge on. Go for it.
10 to the second or 10 to the third between local.
10 to the fifth.
10 to the fifth. So, okay, that's the cost. 10 to the fifth was the cost of processing 10 to the fifth instructions for 1 byte of data if you're transporting over a study at home. How about if the local transport, a local cluster, a local machine?
That's what I meant. That's locally, yeah. There's actually a slide. Thought there was a slide. No. Let's keep going slowly. Yeah, but there was rough equivalence. Yeah, here we go. So you can move 10 terabytes in your LAN. Okay? Or 1 gigabyte in your WAN. So it's 10 to the fifth. Is that right? 10 to the fourth. 10 to the fourth. Okay, let's do that. This is a completely different talk. I mean, completely different. This is what I've been doing, and this is why I've been doing it, and then I'll talk about what I've been doing. And I'll go real fast on this. So in the beginning, there were guys like Ptolemy, who were empiricists. Kepler or Archimedes or somebody started writing down equations for the way the world works. The equations got too complicated. People had to start simulating them. They had computers. 1950, simulation became a third branch of science. The problem that we face now is that Moore's law is working not just for the guys who are doing simulations. Moore's law also works for the guys who build instruments. So people who are physicists who simulate physics experiments generate lots of bytes, but the people who are physicists who build linear accelerators also generate lots of bytes. And so both the simulation people and the empiricists are generating lots of bytes. And this creates a problem which you need software to be able to go through and mine the bytes and look at the data. So in the old days, people would look through a telescope and write down in their notebook what they saw. In the new world, nobody looks through the telescope. The bytes go through a long software pipeline, in this case Fermilab. They come out the other end, land on a disk, and people see the entire telescope through their computer. This just repeats what I said before. Barbar nearby is growing at 1 terabyte per day. The gene sequence thing, it's from another place at Stanford, and you can say that the Space Telescope, there's nobody out there at the Space Telescope looking through the optics on that. That's, okay? So we have Comp X for almost every X. If you go to Stanford, there's computational biology, computational ecology, computational chemistry, computational physics, computational linguistics, okay? And increasingly, there's a bio-info, astro-info, physio-info, people who are trying to understand what the instruments are telling them and are trying to develop algorithms and tools for analyzing and visualizing data. There's lots of it, tens of hundreds of terabytes. Here's the astro-info story. Most astronomy data is on disk somewhere, mostly in FTP servers. It's essentially online. If we could get it organized, we would have the world's best telescope. It would have a picture of the sky in every spectral band from the best instruments. It's up when you're up. If the sun is shining, you can still use the telescope. If it's foggy or raining, you can use the telescope. If the moon is out, okay? And it's a smart telescope in the sense that you can point to a spot in the sky or an object And you can find all the other objects that are like that, and you can find out all the literature about that object. So why is astronomy data so cool? The most important thing about astronomy data is it's absolutely, totally, utterly useless. Okay? It has no privacy concerns. No privacy concerns. The Terra server, we have a picture of your backyard. We've had people send us mail saying, take that picture out of your database. You got a picture of my backyard. You're violating my privacy. Okay? I can share the data with you. You can share the data with me. We can try algorithms. Okay? I've had people come up after this talk and say, come on, we can figure out an IPO based, a startup based on astronomy data. I mean, we're smart people. But no, I have actually never been able to figure out how to make a business out of this. Okay? It is high dimensional, well documented, full of errors. It's real data. This has all the problems of that valuable data that other people want to analyze. Okay? But we can, instead of looking for tanks in the desert, we can be looking for galaxies in the sky. Instead of looking for shopping cart, trends, we can look for clusters of galaxies and the black holes, and we basically can do good science and feel good about it. Okay? It is spatial, it's temporal. These are pictures of the same object taken from different telescopes at different times by different people around the world. Many different instruments, different places, different times. It's the same universe. Barbar is here. LHC is at CERN. There's no desire for the CERN guys to look at Barbar data and no desire for the Barbar guys to look at CERN data. The people don't cross-correlate Barbar and CERN data. It's event data. Another thing about both of those instruments is they're time invariant. The universe doesn't, the Higgs particle was there yesterday, it's going to be there tomorrow. They're looking for it. Okay? They're just as likely to find it here as there. They're not short on data. Okay? The astronomy data has a lot of different properties. It's different spectra, different pictures of the same object at different times, and the universe is changing on all time scales. It's also a great way of teaching astronomy, and it's a good sandbox for data mining algorithms. So I'm a plumber. I do the, let's store the data, get the data out, execute the queries. Okay? This is not drawn to scale. There are a lot of scientists who are out gathering the astronomy data. They need help from the data mining guys to, come up with algorithms that help them find things, and they need to be able to ask questions and visualize answers in a graphical way. Right now, we have one of the worst user interfaces you can imagine. So, I'm not going to show Maria's slides, but you'll be able to see them on the web. I've gone off and visited with many astronomers and tried to figure out what it is they do and done essentially a time and motion study for astronomy. And what astronomers do is they FTP a part of the universe onto their local system, and then they grep it. And they plot x versus y, y versus z, x minus y versus z, x over y minus z, log x times, and so on, looking for things. There are a couple of problems with that. You can grep a megabyte in a second, you can grep a petabyte in 3 years. You can FTP a megabyte in a second, you can FTP a petabyte in 3 years. And it takes a lot of disks after you're done. And at some point, you wish that you had parallelism and you had indices and you had databases. So each of the astronomers who have a big archive have a database problem, and they know it. Okay. I characterize what the astronomers are doing as two kinds of things. They're looking for needles and they're looking for haystacks. Okay? And the paradoxical thing about computers is that computers are really good at finding needles and really bad at finding haystacks. Okay? Different from people. People are good at finding haystacks and lousy at finding needles. But a computer can pick up a piece of straw and say needle or straw in a nanosecond. And so it can go through 1 billion pieces of straw in a second. And you can buy lots of computers. That's an embarrassingly parallel task. Okay? So that's what I mean by it's really good at finding needles. But our haystack algorithms are quadratic and cubic. K-mean clustering, maximum likelihood, correlation, cross-correlation, stuff like that. Okay? And 10 to the 9th cubed is a big number. Okay? And 10 to the 9th is where the astronomers start. They've they found the big haystacks. They know they're galaxies. Okay? Okay? They're looking for unusual collections of galaxies. Okay? They're looking for unusual behavior. So they're looking for haystacks which show up as second-order things, and so they need really good algorithms in this space. And we can prove that really good algorithms are quadratic and cubic, and so we have to go for heuristics. And people are coming up with new data structures and new algorithms in this space, which in fact have dramatically improved the way people can do astronomy. This is the trying to be an icon on the right for move the people or the questions to the data, not the data to the questions. So a lot of what astronomers do is statistical analysis. They're trying to get uniform samples. They're trying to get stratified things. They're basically trying to ask things about the whole corpus. It's much, much better to do all of that processing inside the database than move the database across the network and have it done on the desktop. Yeah.
Share the results of the indices with all these guys, and that's why you wouldn't want to do the move.
Exactly. I'm going to skip over a bunch of these things. Everybody knows what a web service is. If they don't, they'll soon find out. Well, we're trying to build a worldwide telescope. This has failed several times before. People have been trying to build a worldwide telescope for at least 15 years. The astronomers are real smart guys. They know lots of chemistry. They know lots of physics. They know lots of mathematics. They know lots of astronomy, and they know lots of Unix. Okay? I'm serious. I mean, they are really very, very, very good. And they failed. And they failed in part because it's just a big undertaking. But in part, they failed because they haven't had the underlying tools. They tried to build it with X25 or SNA, if you remember those things, or DECnet. Okay? Or, they built, so I think that, grid services and web services and all these standards, having TCP IP, having databases that work. 10 years ago, databases, at least in the Unix space, didn't really work. Some of you remember those days. Some experiments that we did in our group was we made up random SQL queries and we would send them to DB2, Oracle, Informix, Microsoft, and Sybase. And we'd see if we got the same answer back. And my recollection approximately is 95% of the time we got the same answer back from all of them. Okay? But a lot of the times we got back different answers, and and everybody had that experience. That doesn't happen so much anymore. They all more or less give the same answer now. So I am going to probably now just give you a very brief demo of the Sky server and of Sky Query and show you. Okay, so where should I start? I should actually start with the Sky server. So if you go to skyserver.sdss.org, there's a website which we built for the Sloan Digital Sky Survey as a public outreach to teach kids science. And so there's a bunch of science projects here. And you can take an advanced class in astronomy and you can learn about the Hubble diagram. And you will actually discover the Hubble diagram using the data from the telescope. This is a real modern telescope, and here you are using the best data that it's available from a really high quality telescope. And it's going to walk you through how Edmund Hubble found the Hubble diagram, or how found Hubble's constant, and convince people that the universe is expanding. Okay? This is a coffee table atlas. Okay? And you can get these beautiful pictures from the database. And since this is a famous place, you can go off and find all the other data sets that correspond to this famous place. And there's a lot of them. Okay? So this is the 2-mass quick look images and the visual coverage and the IMPRES and the IRAS images and so on. So this is the NASA extragalactic data at Caltech, database at Caltech. And That's what I meant by it being a smart telescope. You can point to a spot in the sky and find all the literature and all the other data sets that cover that spot in the sky. Okay? This data has lots of bugs in it. Here are examples of the kind of bugs you have in the data. Refractions off the side of the telescope, holes in the sky. You'll never know what's behind that star. Okay? There, you can go and you treat this as a telescope. So what we're doing now is we're looking, and I'll just come down here. We're looking at a certain spot in the sky, and I can point to that critter there, and that is a star of the 14th magnitude in the red band. And that is a galaxy. And that is another star. And what's going on here is this mouse click is going out across the internet, going to a web server, and it's taking that XY, which is that mouse click, turning it into an array and a deck, looking in a database, finding the closest star, bringing that back, looking at its magnitudes, creating a little bit of HTML, popping up that little critter there at the top of. And the server, incidentally, is in Johns Hopkins University right now. So and we can zoom in, get a little closer, or zoom out. Okay, and you can use this just like a telescope, right? And you could add this to your notebook. And this is your shopping cart. And this is an internet shopping application, if you think of it. But no, we're going to go and buy that star. So we are now poking around, looking at an individual object. And here is its spectrogram. And you see those things? Those are spectral lines, either emission or absorption lines. Those are those spectral lines in the database. So that cartoon has been parsed into records. Okay? And these are the guys redshifted. And here are the photographic object. That was a spectrographic object. Here are the 400 attributes of that critter. Okay? And this is the neighborhood he came from, and so on. And you get the idea. And we can go off to the Ned search, and we can download things, and we can cross-index to others, et cetera. Okay? Let's cut down, throw away some of these windows. But now we're going to go from pixel space to set space. I started out poking around in pixel space. I then poked at a particular object and looked at a particular record in the database, or a particular object in the database. What we're now going to do is find all the objects at a certain spot in the sky, RA and DEC, certain radius, and we can set up a color cut, but I'm just going to take the default. And that form generated that SQL statement. And that SQL statement generated that answer. And now we can take that SQL statement. I told you we had bad user interfaces. And we can ask for all of the critters rather than just the first 10. And there they are. And there's several hundred of the guys. Okay? And these are their attributes. And we actually allow both students and astronomers to ask SQL queries of this database. So this is remember I said you don't want to give people SQL access to your data? Well, these astronomers want to have ad hoc questions, and they learned Perl, they learned Java, and they're willing to learn SQL if they get the answers they want. And in fact, they've been shown a surprising willingness to learn SQL in order to get answers back. Okay? There's a bunch of other stuff here about documentation. Let's see. I'm going to skip over that and take you to the discussion of SkyQuery, and then I'll stop. Okay, so that was the discussion of the Sky server. And I took you through pixel space and record space and doc space, which is the documentation, sets of records. I didn't show you the web query logs. The web query logs are online. And I didn't show you the web service. But you can download a personal edition of that database from my website. And so that database comes in the enterprise edition, which is terabytes. Okay? The professional, I'm sorry, excuse me, the departmental edition, which is gigabytes, and the professional edition, which is 1 gigabyte, which fits on your laptop. Okay? And let's not go, okay? I'm not going to show you the cutout service right now. So SkyQuery is an attempt to federate many archives. Okay, so I showed you, what we were looking at was one telescope. SkyQuery is an attempt to take radio, infrared, ultraviolet, and optical surveys and glue them together and let you ask questions of them. Okay? So again, it's going to be one of these horrible SQL query interfaces. It's done by these guys at Caltech. Here's a cartoon of the way it works. There's a web service here, a web service here, a web service here, and a web service in Cambridge, England, Isaac Newton Telescope. You go to the interface and you ask a question. When you ask a question, implicitly what happens is they say, okay, we have 4 telescopes in this picture, I think, 4 telescopes. You're asking a question. What we're going to do is implicitly join the data from those 4 telescopes together, doing a so-called Bayesian spatial join. Let me walk you through those words one by one by one. Okay? What's a spatial join? Okay, so we got an old database over, or old telescope over here, and this is how big its error circle is. So everything in this circle, it's this big around, looks like one object. We got this modern new telescope over here that's its error circle is like this. And this telescope sees 8 objects in this circle. Those 8 objects correspond to one object over here. Okay? So you think of, for every survey, when somebody sees something, it's essentially a Gaussian, or a point spread function, around a certain point. And the diameter of that Gaussian, or its sigma, standard deviation, is a property of the telescope. So we now take the Gaussian of this guy and the Gaussian of this guy, and we intersect them. That's called a Bayesian kind of thing. Okay? And if the area under that curve, the intersection, is above a certain threshold, we say, this is the same object. Okay? So now I'm going to go back one slide, and I'm going to show you the cross match between O and T is less than 3.5. Okay? And that means that they're less than 3.5 sigma apart. So it's a very loose cross match. Okay? So this portal here takes in the query, teases it apart, figures out what has to be done, sends the question to each of these guys, okay, saying, how big would your answer be? Doesn't ask it for the answer. It says, how big would your answer be? And then it sends the query in a way so that the smallest answer goes to the next biggest guy, and it goes to the next biggest guy, so that the answer slowly grows. Okay? So the query actually gets executed twice. And this is all done with XML, all done with web services. It's amazing. Okay? Now for the demo. With any luck at all, it will be up. SkyQuery. SkyQuery.net. Okay, we can try query number 3. Pretty easy. Okay, so select objects from either TOMAS or FIRST, cross-match. This is the thing that was in the slide, and the area of the sky is in this, and the type is 3, which says it's a galaxy. Okay, we submit that query. Ooh. Okay, the thing that's astonishing about this is that it works at all. Okay, if you knew what was going on here, I mean, XML, web services, queries being run twice, I mean, this is an outrageous system design. Okay? But I'm challenged to come up with a better one. Okay? Here's one that's a transcontinental join. This is something the database guys have been talking about for years. Okay? This is not just a transcontinental join. This is a transatlantic join. Okay? This is Cambridge, England, and Baltimore, Maryland. Okay? Submit that query. That's amazing. Okay? And there is the records from Cambridge and from Baltimore. Okay? And so, you know, I mean, you say, well, how does this work if I move around terabytes? Well, it doesn't. How does this work if I don't move around terabytes? Well, it works really great, as you can see. Okay? So going back to the PowerPoint. Oops. This is a data grid. This is not a computation grid. We're moving objects around. We're moving questions and answers around. Okay? It works today. There's this thing called OGIS, Oxidai, I think is the way it's pronounced. OGSA or I, DS, Oxidai. And this is databases meet the grid. And Hello World in Oxidai is about 350 lines. And Hello World in this .NET stuff that this was always built with is more like 37 lines. This is not a lot of lines of code that we're looking at here, which is really surprising and very pleasant. Okay? What we're doing now is the portal, we're adding a web service, a web interface that allows you, and you can go there and do this tomorrow, to create your own database. So you can create your thing called MyDB that lives here. And now you can run your queries and build your workbook here in the fat side of the internet where people have lots of bandwidth. Okay? And bring your answers back as needed. And I think with that, I'm going to stop. I wasn't sure how long the talk was going to go, so to summarize, though, we are building the Worldwide Telescope. It is a lot of fun. As I said, the reason it's so much fun is the data is completely, utterly useless, so there's never any discussions about, I mean, when I work with the bioinfo people, there are all sorts of problems about, well, how are we going to make money at this? Astronomers never ask that question. Okay? And so it means that we're just doing science. Okay? And that is, frankly, a lot of fun because it means we can work on technical problems, which I think, incidentally, have huge economic value. But they can be done in a context that's much more free and open. And the Oracle guys and the DB2 guys and the Microsoft guys can all talk together and cooperate and work on this and interoperate. And it's a great sandbox to play in.
20 minutes for Q&A. And there's a microphone on each side of the room that we'll try and sort of hand around in the order in which you raise your hands.
All right, thank you. Hello?
I can hear you.
Okay.
I'll repeat the question.
Hello? Oh, it's working now. So my question is is there some place that I can go to learn about what you're doing here and apply it to commercial enterprises? Because
sure,
we have exactly the same problems that you're having in the science field.
Sure. So everything I do is public. All the code I've written, I can send it to you, or actually I can give you the URL and you can download it.
I'm looking more for papers and books that will kind of, because
I've been writing stuff like There's No Tomorrow, but there's a lot of stuff we haven't written down. But the database design is well documented. The website itself is actually pretty self.
Okay.
And parenthetically, I'm in San Francisco. You're in Silicon Valley.
Drop by. Take you out to lunch.
Well, that's the bad news. When you come to my place, I have to buy. That's good.
Hi, I was wondering if you could comment on how you think the prices of telephone service are going to collapse. And in particular, do you think one country or another is going to figure out first that its phone company is bankrupt?
Well, people tell me that bandwidth in Singapore is very, very inexpensive, and that bandwidth in South Korea is very, very inexpensive, and that virtually everybody has fiber to the home in Singapore, and many people in South Korea have fiber to the home, and that the pricing in those two countries is different. I don't know how it's, I don't understand how it's held up this long. Okay? So I'm not the right person to comment. I can't say anything. You look like you're an old guy too, right? I mean, we've been watching this for quite a while, and it's amazing. And one person explained to me that phone companies' core competence is lobbying. And that sentence probably explains more of the way things are than anything else I can think of.
Well, the only thing I can add to that is when I took networking from Van Jacobson, he just sort of like said he looked at WAN and he said that was awful, and he spent most of his career in LAN.
Mm-hmm.
Thank you.
Mm-hmm. And now the stunning thing is that, at least where I work, the WAN is faster than the LAN. And what I mean by that is that we actually do have a few OC192s poking out of our data center. And there's nothing in our data center that runs at 10 gigabit. And it's really paradoxical. And we are in the process, as many other people are, of setting a LAN speed record where we're sending stuff at 10 gigabits coast to coast. And it's hard to find local infrastructure that's as fast as the WAN. So there's some interesting things about the way the world is right now, which don't make a lot of sense, at least to me. And I've talked to other people who they should make sense to when they say, lobbying is the core competence.
So actually, Jim, I had a conversation with you about 16 years ago, and you had an interesting observation then, and I wanted to kind of follow up on it. At the time, you went on and said that, well, I'll remind you of it. At the time, you went on and said is that, memory is getting cheaper and cheaper, and we're going to have lots and lots of memory inside the CPU, and now the question is going to come up is with all this memory that's going to be sitting inside the computers, what kind of applications could we possibly come up to consume all the memory that comes in? So, besides letting Microsoft have new operating system releases, I was wondering, what you saw happen with that stuff, and in fact, how that memory was used up in your opinion.
It is the case that RAM has gotten extraordinarily cheap, and I'm stunned at how inexpensive it is. 4 gigabytes, I think, is now something like in the $250 range. I mean, it's $80 a gigabyte, if I'm not mistaken. So actually, it's probably more like $300 for 4 gigs. So all of a sudden, you really need 32-bit addressing. Databases are a good use. Databases work really well when they don't have to go to disk. One of the things remember I said that the disks are getting bigger and bigger and bigger? Okay. If you think about why you wait, when your computer boots or when you launch an application or when you open a file, why do you wait? You're not waiting for the CPU. Okay? You're waiting for the network or you're waiting for the disk. I spend most of my time waiting for the disk. Most of the data mining I'm doing is limited by disk bandwidth. Okay? So to the extent that I can prefetch and cache and keep my indices in main memory, I'm way ahead. So I think what the main application I see for large main memories is cutting down disk latency. Okay? For applications which are battery powered, it will be keeping the disk turned off because the disk is a power hungry thing compared to the corresponding amount of RAM that you might need. So many MP3 players do this. And the other thing is for data mining, these n-squared algorithms and n-cubed algorithms, they really work a lot better if you aren't doing n-squared to the disk, but are doing n-squared to RAM.
I wanted to ask you, I mean, I thought in the first talk that you gave, you were just saying that you didn't think that grid computing was very useful in many cases, but then in your second talk, you talked about building this data grid and what a wonderful thing that you can do with it. How do you reconcile these two?
Well, the first one I said that harvesting CPU cycles, which is what the computation grid is, doesn't seem like a terribly good economic deal to me unless someone else is paying the phone bill. Okay? And so computation grid. And I distinguish computation grid from data grid. Data grid, you move the question to the data. Okay? Computation grid is MPI programming where for various reasons we can only have a $100 million computer in San Diego. But people in Illinois have a $100 million computer, and the people in Pittsburgh have a $100 million computer. So we have, between the three of them, a $300 million computer. And if we could just extend the backplane, transcontinental, we would have a really powerful machine. And our applications would work if the speed of light were a little bit faster and if the phone bill were zero. And I look at that argument and I say, I can think of other ways of solving that problem. And it would be cheaper, actually, to put the $300 million computer in one place. And so it's the relative cost of WAN and LAN bandwidth. And it is for tightly coupled computations, it absolutely dominates the cost of the computation. One of the things, well, I should just stop. question is there are various cost-benefit functions associated with computation. If you want to solve QCD, quantum chromodynamics, wait 100 years, and it will run in 5 minutes on your kid's toy. Okay? Okay? Or wait 10 years, and it'll run on your departmental system. Or start right now, and it'll take 10 years to finish. Okay? Okay? So, you know, I mean, it's one of these things where, you know, well, enough said. So if it's urgent that you have the answer, then the cheapest way of getting the answer is you can trade time for money. Okay? So you could spend a lot more money and get the answer sooner. Okay? And one of the things that's wrong with my analysis, and I'm embarrassed by it, is I don't know how to measure all the costs I don't know how to measure. And I don't know how to measure the cost of people in particular. I can measure all of the things that are tangible, but the organizational costs I don't know how to measure. So I just ignore them. Okay? And that's simply wrong. And so you can easily come to wrong conclusions by doing the kind of analysis that I have done. And I hinted at that when I said, when you look at the actual networking cost that I pay, the phone bill is a small part of it. Somebody over here had a question.
I worked on the Teradata system, you know, the
Teradata? Mm-hmm.
Yeah, and you know, we had good scalability because we went
fantastic, right?
Sideways, and I was wondering why do you think there wasn't much, you know, open source development in that area using commodity PCs to create distributed databases?
Teradata was the first of the data mining, massively parallel databases. It wasn't very good for online transaction processing, but was great for looking for needles in a haystack. Had a SQL interface, and the standard Teradata product was somebody had a great big IBM mainframe, and they would roll in a Teradata, and the Teradata would plug in and replace the DB2 interface and run a lot faster and a lot cheaper. And gradually, people started using Teradata on its own. Tandem and Informix did a incredible job of cloning the Teradata ideas and have done okay with their products. I've been working at Microsoft for about 6 or 7 years, and I've been trying to help the Microsoft guys clone those ideas. And so far, we've failed. It's not easy to do what Teradata did. The open source guys are typically characterized by Postgres or MySQL, are working on the much more, or SleepyCat, are working on the much more basic, let's add transactions, let's add referential integrity, let's add, you know, data types, let's add replication. And so they're working on the more basic things rather than the, which show up in web applications and online transaction processing, and are less focused on the data mining decision support part of databases. I think that will come with time, so the simple answer is it's hard to do what Teradata did. And the Teradata guys took a really radical approach of hashing everything. The great line is, if it's not organized, it can't get disorganized, and it never needs to be reorganized. I'll say that again, because it's really, Gary Hallmark made this observation. If it's not organized, and hashing is not organized, it can't get disorganized, and it never needs to be reorganized. Okay? So, you know, they basically just spread the data out at random across all of the devices. If new devices are added, they rehash. DB2 and Informix copied those ideas, as did Tandem. And then they just search those hash buckets in parallel. And it's a very nice design, very simple design, but it's hard to execute that design faithfully, especially if you have a large legacy of OLTP this and, you know, TPCC results and, you know, all that sort of stuff.
Thank Jim for
Thanks for having me.
pair of talks tonight.
Thanks for having me.